Our next force is going to be the normal force. And its symbol is going to be little n. And the normal force is basically a supporting force. A force between the two solids that are touching each other. How about I just call it a supporting force between two solids. So I can push on the paper, which, I'm pushing on the document camera here. And my hand doesn't go through the document camera. And the document camera doesn't go through my hand. And so I can feel myself pushing on this piece of equipment. And it's the normal force that I feel. So you can push on a wall. That would be a normal force. You can sit on a chair. The force between your bottom and the chair is the normal force. If you stand on a floor, right, it's the floor supporting you between two solids, your feet and the floor, right? So that's going to be the normal force as well. So the normal force, and I can't give you an equation just to calculate the amount of this again. The amount really depends on the situation. But the direction is going to always be perpendicular to the surface, which is why it's called the normal force. In math class, normal means perpendicular. So the normal force is always perpendicular. It's defined that way. So if I had a book sitting on a table, they press against each other. So we could say that the book would feel an upwards normal force from the table. Let's say table acting on book. And kind of like we discussed before, forces occur in pairs. So if the book is pressing on the table is pressing on the book. So we could also say that there's a normal force that the table feels downwards, and that would be the book acting on the table. And you notice that the surface between them is horizontal, so the normal force has to be vertical. What about a box on a ramp? Since the surface is at an angle, the normal force between those two solids has to be perpendicular to that. So the block would feel a normal force supporting it this way. And because of that, the table or the ramp would feel a normal force this way. So this one would be block acting on ramp, pushing it kind of down and inwards. And this one would be the ramp kind of supporting the block. And then let's do a little bit more. Just introduce this idea for a second. Let's say we have a frog sitting on a table. And then a frog sitting on a table, well, it's kind of extending its legs, jumping in the process of jumping. Look, there's my frog, right? Frog sitting on table. And this is going to be frog while jumping. If the frog's going to sit on the table, that means the table's supporting him. So the frog will feel an upward normal force because the table's supporting him. But how does a frog jump? The frog jumps by pushing into the table even harder, and that means that the table will push back on the frog to match it. So the normal force increases when the frog is jumping. When the frog is pushing against the table harder, there is more normal force. And if we wanted to be thorough, we could also say that the table would feel an equal and opposite force as well. So this could be the normal force of table acting on frog, frog acting on table, these would have to be equal and opposite due to Newton's third law, and same with those. Static friction is going to be friction that acts between two objects that are kind of stuck together, that are not sliding over each other. Our abbreviation for that is going to be a little f for friction and then a little s for static. So let's go back to a ramp with a block on it. Now, if this ramp was icy, then the block would just slide down the ramp. So why doesn't it slide down the ramp? Why can't it just sit there? And it's going to be because of friction. And since it's just sitting, we'll call it static friction. Now, static friction will always act parallel to the surface, and it's going to always act to prevent the slip. So if it was ice, it would slip down the ramp. So static friction is going to act up the ramp, parallel to the surface. And it's going to be the ramp acting on the block. And so you can see that the surface here between the two objects is in this direction. So the static friction force also has to be aligned in that direction. Now you could imagine tilting the ramp even steeper, and perhaps it hasn't slipped yet. So in that case, static friction would end up being larger to prevent the slip. But there is a point, right, where you tilt the ramp high enough and then the block will slip. And so static friction is going to have a maximum value, and then you can just overcome it. So let's say this. Static friction can be any value between 0 and the maximum amount. And then the direction will always be parallel to the surface to prevent the slip. There is a way to find the maximum amount. We do have an equation that would help us get that. And so that would be the maximum static friction value. And that is going to be equal to a coefficient called mu s times the normal force. And so mu s, so first of all, that's the Greek letter mu, is going to be the coefficient of static friction. And it's really just going to represent the materials. Is it ice sliding over ice? Then this will have a low value because it's easy to slip on ice. But if the materials are stickier, like rubber trying to slide over rubber, like rubber shoes on a rubber gym floor, then it'll have a high value. Those materials are stickier. And usually what you can just do is look up this value in the back of your textbook. There's a little table. All right, so the next type of friction is going to be kinetic friction. And remember that kinetic is supposed to mean motion. So this is going to be friction between two objects that are sliding over each other. And our abbreviation is going to be F with a little k. So let's maybe take that ramp that I had drawn before and draw it much steeper. And imagine that the block is slipping down the surface, sliding down. Now I'm imagining like a wood block over a wood ramp. And so there is going to be some friction. So in that case, the friction is going to try to prevent the slip or try to slow it down. And make sure that your friction arrow is, again, parallel to the surface. So, kinetic friction is going to be equal to coefficient of kinetic friction, so it's going to be a little mu k, times the normal force. And it's going to always act in a direction parallel to the surface. In a direction to try to stop the slip. So N is the normal force, and that's the supporting force between the two materials, which we had talked about earlier. And mu k, and again that's that Greek letter mu, is going to represent the coefficient of kinetic friction. And just like the static friction, all it does is kind of specify which materials are involved. Is it an ice block sliding over an icy ramp? Is it a wood block on a wood ramp? It describes the stickiness of the materials. So here is the table from the back of your book. So a problem might say there's a wood block on a wood ramp, and you would have to come back here and find the value. It's not going to tell you that there's kinetic friction or static friction. You would have to identify that just from reading the problem. And then you could come back and say, oh, I have a wood block on a wood ramp, and you would use this value, the static coefficient, if it was not sliding. And you would use the kinetic value if it was sliding.
So here I have my whiteout. So let me slide this across the paper a little bit, and it should come to rest because of friction. Okay. But friction can also speed it up. What about if I move the paper underneath it? The paper can kind of grab on to the whiteout there with a little bit of friction and bring it along with it. So be careful that friction doesn't always slow things down. Friction can speed things up. What friction tries to do is prevent the slip between whatever two objects you're talking about. And remember, friction has a limit, so if I move this paper too fast, it won't have enough force to actually move this whiteout fast enough to keep it up with the paper. But as long as I'm moving the paper slow, the paper can speed up the whiteout. Let's write something down to that effect. Friction doesn't slow things down. It tries to prevent or reduce the slip
of two objects over each other.